Galactic magnetic fields are born from motion. As charged particles drift through gas and plasma, the slow spin of a galaxy combined with restless turbulence ignites a cosmic dynamo. What begins as a faint whisper of magnetism is strengthened over billions of years, until invisible lines of force thread through entire galaxies. The magnetic patterns we observe today are the long memory of that ancient amplification. These fields quietly shape destiny. They resist gravity's pull, bracing gas clouds and slowing their collapse into stars. They also guide matter into elongated strands, sculpting the interstellar medium into filaments and veils. Detecting such subtle forces across vast distances is difficult. Astronomers listen instead to radio light. When energetic particles spiral along magnetic lines, they emit radio waves with a preferred orientation. Mapping that polarization reveals the hidden geometry. A second method watches how polarized signals from distant sources twist as they pass through magnetized gas, a phenomenon known as Faraday rotation. Together, these techniques show that galaxies like the Milky Way and Andromeda possess large-scale magnetic fields, measuring only a few micro-Gauss feeble compared to Earth's field, yet powerful enough to influence galactic evolution. Spiral galaxies also carry chemical signatures etched into their disks. Astronomers call this metallicity, the fraction of elements heavier than helium. In spirals, metallicity is highest near the core and steadily declines toward the outskirts. This gradient tells a story of growth. Galaxies appear to build themselves from the inside outward. Their central regions ignited first, cycling through many generations of stars and steadily enriching the gas. The outer disk formed later with fewer stellar generations and less chemical buildup. Fresh gas falling into a galaxy usually arrives poor in heavy elements. It settles mostly in the outer disk, diluting the metals already there. Star formation is also less efficient at these distances, further slowing enrichment. In the Milky Way, this pattern is clear. Our Sun, orbiting about 26,000 light-years from the center, carries a metallicity typical for that radius. Stars closer in are richer. Those farther out are poorer. Yet the gradient is not perfectly smooth. Irregularities betray ancient gas flows, wandering stars, and localized bursts of creation. By charting these variations, astronomers test how the Milky Way assembled itself across time. Andromeda shows a similar chemical slope, though distance blurs the details. Future infrared eyes, such as the James Webb Space Telescope, will sharpen that view and trace Andromeda's enrichment with far greater clarity. Smaller galaxies tell a different tale. Dwarf systems are too modest to sustain strong gradients. Turbulence and stellar feedback mix their gas thoroughly, leaving metals spread more evenly throughout. To truly grasp the meaning of these patterns, we must look back to the universe's awakening. After the Big Bang, there was a long silence, no stars, no galaxies, only hydrogen and helium drifting in darkness. This era, often called the Cosmic Dark Ages, ended when the first stars ignited. These primordial giants burned hot and brief, flooding their surroundings with ultraviolet light. Around them, bubbles of ionized gas formed and expanded. As more stars were born, the bubbles merged, until roughly 1 billion years after the beginning, the universe was transformed. This was the epoch of reionization, a turning point written into cosmic history. The faintest dwarf galaxies in the local group are survivors from that sacred threshold. They formed their stars during or soon after reionization, and then fell silent. Their ancient stars preserve a record of those early conditions, like embers from the first fire. What powered reionization remains an open question. Were the first massive stars the primary source? Did early quasars contribute, their black holes blazing as they fed? Evidence favors starlight from young galaxies, but the balance is still debated. Reionization did more than light the universe, it reshaped destiny. The same ultraviolet glow that stripped electrons from atoms also heated gas, making it harder for small structures to collapse. Star formation in low-mass halos was suppressed, likely freezing the evolution of ultra-faint dwarfs before they could grow. By reconstructing their star formation histories, astronomers can constrain when reionization unfolded and how deeply it altered the smallest galaxies. The local group is therefore not merely a gathering of nearby galaxies, it is a proving ground. Because of its closeness, we can resolve individual stars, measure their ages, trace their motions, and read their chemical signatures in detail impossible elsewhere. In doing so, we uncover a deeper truth. These galaxies are witnesses. They carry the memory of the universe's first light, the forces that shaped it, and the quiet laws that continue to guide the chosen structures of the cosmos toward their unfolding fate. The nearby universe allows us to read motion as clearly as light. Then the local group, astronomers can track how stars and gas move, tracing invisible structures that would otherwise remain hidden. From these motions, the distribution of dark matter is revealed, and competing ideas about its nature are put on trial. Faint stellar streams and ghostly shells echoes of ancient mergers merge from the darkness. Such fragile remnants are far too subtle to be seen in distant galaxies, yet here, close to home, they stand exposed. We can also witness galaxies in the act of creation. Individual star-forming regions can be resolved. Cold molecular clouds can be mapped. The texture and phases of the interstellar medium can be measured directly. This level of detail turns the local group into a proving ground. Theories of galaxy formation are not judged by elegance alone, but by whether they survive confrontation with these nearby truths. If a model fails here, where the evidence is richest, it cannot hope to explain the wider cosmos. Environment leaves fingerprints as well. The local group allows careful comparisons. Satellites of the Milky Way set against those of Andromeda. Isolated dwarfs contrasted with companions crowded by neighbors. Differences in gas content, star formation, and survival reveal how surroundings shape destiny. In this way, the local group becomes a miniature version of the universe itself. A small stage upon which the same physical laws play out on a grander scale elsewhere. Progress in understanding this cosmic neighborhood has come in sudden leaps, each unlocked by new technology. One of the most transformative moments arrived in the early 2000s with the discovery of ultra-faint dwarf galaxies. Though close by, these systems were invisible until digital sky surveys, such as the Sloan Digital Sky Survey, swept the heavens with unprecedented depth. What they uncovered was astonishing. An entire population of galaxies hiding just beyond the limits of human sight. Finding them required ingenuity. Astronomers searched vast star maps for subtle excesses, tiny clumps, where stars appeared slightly more numerous than chance would allow. Such overdensities might signal a hidden galaxy, but appearances deceive. Some are random fluctuations, others are star clusters or fragments torn loose by tides. Confirmation demands motion. By measuring the velocities of individual stars, astronomers can see whether they move together as a bound family. Shared motion is the signature of a true galaxy. This task is formidable, requiring spectra from stars so faint they hover at the edge of detectability. Yet modern instruments on large telescopes have risen to the challenge, capturing the motions of stars as dim as 20th magnitude and beyond. Another revolution came with the ability to measure proper motions, the slow drift of stars across the sky. This breakthrough was delivered by the Gaia mission, which charted the positions of billions of stars with exquisite precision. By comparing Gaia's measurements over time, astronomers can reconstruct full three-dimensional motions for nearby dwarf galaxies. Not only how fast they approach or recede, but how they slide sideways through space. With this knowledge, the past and future paths of satellites can be traced. We can tell whether a dwarf galaxy is making its first descent toward the Milky Way, or whether it has circled before, battered by repeated encounters. These motions also tighten estimates of the Milky Way's dark matter halo, revealing its true weight. Chemical insight has advanced just as dramatically. Today's spectrographs can measure dozens of elemental abundances in individual stars, allowing astronomers to reconstruct a galaxy's chemical ancestry in fine detail. Stars that once belonged to the same parent system can be recognized by their shared chemical fingerprints, even after being scattered across the sky. Among the most powerful beacons in this work are RR Lyrae stars. These ancient pulsators beat with clock-like regularity, brightening and dimming over half-day cycles. Their intrinsic brightness is well known. By identifying our Lyrae stars within a dwarf galaxy, astronomers can determine its distance, gauge its age, and infer its metallicity with remarkable confidence. Even the study of tidal streams, the long, delicate trails left by disrupted galaxies, has been transformed by these advances. Together, these tools have turned the local group into a living archive, where motion, chemistry, and light converge to reveal how galaxies are born, altered, sometimes unmade, under the quiet governance of cosmic law. These stellar streams are whispers stretched across the sky, long faint, and easily lost against the cosmic background. Yet by weaving together many kinds of evidence, astronomers have learned to hear them clearly. Wide-field surveys provide deep photometric maps. Spectroscopy reveals the velocities and compositions of individual stars. Gaia's precise proper motions add the final dimension of motion. Together, these threads allow scientists to separate true stream members from unrelated foreground and background stars with remarkable confidence. Once revealed, the streams become powerful probes. Their thickness, density, and changing velocities along their length are carefully measured. From these patterns, astronomers can retrace the path of the long-destroyed parent galaxy and infer the unseen shape of the Milky Way's dark matter halo. In this way, streams act like cosmic calligraphy, writing the history of gravity across the heavens. Radio eyes add another layer of insight. Neutral hydrogen, glowing faintly at a wavelength of 21 centimeters, betrays the presence and motion of gas throughout the local group. These maps show a clear divide. Irregular dwarf galaxies still cradle rich reservoirs of gas, while dwarf spheroidals are almost entirely barren. Their gas has been stripped away by environment and interaction, silencing star formation long ago. This is no longer speculation. It is written plainly in the radio sky. The gas itself is not smooth or simple. High-velocity clouds streak through the halo, moving in ways that defy the orderly rotation of the Milky Way's disk. Some appear to be the torn remains of satellite galaxies. Others may be fresh material flowing in from intergalactic space. Together, they hint at a galaxy that is neither closed nor static, but breathing, losing, and gaining matter over time. Infrared vision opens yet another hidden realm. Many old cool stars shine weakly in visible light, but glow clearly in the infrared. With the James Webb Space Telescope, astronomers can now study these ancient populations in extraordinary detail. Dust that once obscured star-forming regions becomes transparent, and the earliest stellar generations in the local group can be examined, their properties tested against theories of how stars live and die. Ultraviolet light, by contrast, reveals youth and fury. It highlights the hottest, most massive stars and marks the regions where star formation rages most intensely. These observations even identify stars on the brink of destruction, soon to end their lives as supernova. X-ray observations complete the picture by exposing the most violent processes of all, supernova remnants. Neutron stars, black holes, and vast halos of gas heated to millions of degrees by shocks and radiation. Each wavelength tells a different truth. Together, they form a unified vision of local group galaxies, one that places strict limits on any theory that seeks to explain their origin and evolution, yet observation alone is not enough. To truly understand the local group, astronomers must also create universes of their own. Sophisticated simulations attempt to replay cosmic history from its earliest moments. They begin just after the Big Bang, using patterns imprinted in the cosmic microwave background, tiny ripples and density that seeded all later structure. From these beginnings, the simulations let gravity work its slow miracle. Dark matter halos condense. Gas falls inward, cools, and ignites into stars. Stellar winds and supernova inject energy back into their surroundings. Halos merge, collide, and grow, assembling galaxies over billions of years. To follow this process across 13 billion years of cosmic time requires staggering computational power. The largest simulations track billions of particles and run for months on supercomputers with thousands of processors working in unison. Their achievements are profound. Modern simulations can reproduce the broad features of the universe we observe, galaxies of the right sizes and masses, realistic star formation rates, and the vast cosmic web of filaments, clusters, and voids. But these digital universes are fragile. They are only as faithful as the physics written into them. One of the greatest challenges lies in modeling star formation itself. The birth of stars unfolds on scales of light years or less, far below the resolution of cosmological simulations, which operate on scales hundreds or thousands of times larger. To bridge this gap, astronomers rely on subgrid prescriptions, simplified rules that stand in for complex, unresolved physics. These approximations are necessary but imperfect. And so the work continues. Observations, refined simulations. Simulations guide observations. Between them, the local group stands as both teacher and judge, a nearby testament to whether our stories of cosmic origin are true, or merely convincing shadows cast against the dark. Yet another veil of uncertainty lies in the way simulations handle feedback, the cosmic response to the birth and death of stars. When stars ignite, they do not form quietly. They pour out radiation, drive powerful stellar winds, and in their final moments, massive stars tear themselves apart as supernovae. Each of these events releases vast energy into the surrounding gas, heating it, stirring it, and at times, casting it entirely out of the galaxy's grasp. This process is not a detail, it is a governing force. If feedback is modeled too aggressively, simulated galaxies emerge stunted and starved, forming too few stars. If feedback is too weak, galaxies grow bloated and overgrown, far more massive than reality allows. Different simulations attempt to walk this narrow path in different ways. Some inject energy as heat, others as motion, giving gas a sudden kick. Some include the push of radiation from massive stars. Others add the influence of supermassive black holes, whose feeding can flood a galaxy with energy. That these differing approaches yield different outcomes is itself a revelation. It tells us that while feedback is essential, its true nature is not yet fully understood. We know it shapes galaxies, but we are still learning exactly how. Even so, modern simulations have achieved remarkable successes. They predict that a structure like the local group should contain two dominant galaxies surrounded by dozens of smaller companions, precisely what we observe. They also predict that these satellites should be overwhelmingly composed of dark matter, another point of agreement with reality. Yet harmony is not complete. Some long-standing tensions remain. Simulations often predict more satellite galaxies than we observe, a puzzle known as the missing satellites problem. Others produce dwarf galaxies whose centers are too dense compared to observations, touching on the Corcus problem. Still others allow small galaxies to keep forming stars far longer than real satellites appear to have done. Each mismatch is a signpost, pointing toward missing or imperfect physics. Resolving these tensions demands progress on two fronts at once. Sharper observations to pin down the true properties of dwarf galaxies, and more refined simulations that better capture the complex interplay of gravity, gas, radiation, and feedback. One promising path forward is the creation of simulations designed specifically for the local group. Rather than modeling a random slice of the universe, these efforts begin with carefully chosen initial conditions that are meant to give rise to a Milky Way-Andromeda pair. This targeted approach allows much higher resolution and a far more detailed reconstruction of the local group's history. Such simulations can make concrete, testable predictions. How many tidal streams should lace the halo? How satellite galaxies should move? How dark matter should be distributed, and when different galaxies should have formed their stars? Observations can then serve as judgment, confirming or challenging the simulated outcome. Simulations also act as interpreters of mystery. When a dwarf galaxy shows an unusual orbit or a strange pattern of star formation, numerical experiments can explore possible causes. Was there a close gravitational encounter? A sudden loss of gas? A long fall through the Milky Way's halo? In silico universes allow these questions to be asked and, sometimes answered. With our dead-eyed. The story of our galactic neighborhood is inseparable from the story of the universe. In the earliest instance after the Big Bang, Tiny quantum fluctuations were stretched to enormous scales during a brief but dramatic phase of expansion known as inflation. Those minute variations became the seeds of all structure. Slightly denser regions drew in matter and grew ever richer. Slightly emptier regions became vast voids. Over billions of years, gravity sculpted these initial imprints into galaxies, groups, clusters, and superclusters. The local group is one such outcome, a fossil of primordial physics made visible. Its mass, scale, and surroundings were written into the universe at birth and shaped by laws that have ruled ever since. By studying the local group in exquisite detail, we are not merely learning about nearby galaxies. We are testing the foundations of cosmology itself. Even the nature of dark matter is bound to this quest. The number of satellite galaxies around the Milky Way depends on what dark matter truly is. If it consists of weakly interacting massive particles, one pattern emerges. If it is made of ixions, another. By counting satellites and comparing them to theoretical expectations, the local group becomes a measuring instrument, a quiet but powerful judge of the universe's hidden substance. Taken together, the satellites of the Milky Way act like test particles in a vast, invisible gravitational field. Their motions encode information about the shape, mass, and extent of the Milky Way's dark matter halo. By measuring their orbits in 3 dimensions and comparing them with simulations, astronomers can rule out some dark matter models and favor others. A halo that is too round, too flattened, too centrally concentrated, or too diffuse leaves a distinct imprint on satellite motions. In this way, the small galaxies around us become precision instruments for probing physics we cannot yet reproduce in laboratories. The same is true of their star formation histories. When stars formed or failed to form in local group galaxies depends on conditions set by cosmology itself. The timing of reionization, the efficiency of cooling in primordial gas, the clustering of dark matter on small scales, and the nature of the first stars all shaped when galaxies could ignite. By reconstructing these histories star by star, astronomers effectively read a fossil record of the early universe written into nearby galaxies. The local group also plays a quiet but crucial role in one of the most important debates in modern cosmology, the expansion rate of the universe. Different methods for measuring this rate currently disagree slightly, a tension that could hint at new physics or unrecognized systematic errors. Because the distance ladder begins locally, its lowest rungs must be exceptionally well calibrated. Distances to stars and galaxies in the local group anchor the entire structure. Any error here ripples outward to cosmological scales. This is why extraordinary effort is devoted to measuring precise distances using key fights, our Lyrae stars, eclipsing binaries, and geometric techniques. The local group is not just nearby, it is foundational. At the same time, it is one of the most promising arenas for uncovering the true nature of dark matter. Dwarf spheroidal galaxies, with their extreme dark matter dominance and relative lack of astrophysical clutter, are among the cleanest targets for indirect detection searches. Gamma-ray and neutrino observatories have scrutinized them for telltale signals of particle annihilation or decay. So far, the universe has remained stubbornly quiet, but silence is itself informative. Each non-detection narrows the space of viable theories, guiding future experiments toward greater sensitivity or entirely new strategies. None of this diminishes the mystery. Dark matter may interact even more weakly than we expect, or in ways we have not yet imagined. It may not annihilate at all. Or it may reveal itself only through subtle gravitational effects. The local group remains central to all of these possibilities, because understanding where dark matter is and how it behaves on small scales is essential for knowing where and how to look. Despite decades of progress, the local group still guards many secrets. We do not yet know its full census. Ultra-faint dwarfs may lurk behind the dense star fields and dust of the Milky Way's disk, or drift quietly at the group's outskirts. Each new discovery refines our understanding of how galaxies form and how dark matter sculpts structure. We also do not yet know what ultimately quenched star formation in dwarf spheroidal galaxies. Was it the ultraviolet bath of reionization, the violence of early supernova, the stripping effects of their massive neighbors, or some combination of all three, acting at different times? Untangling these influences will require deeper observations and more realistic simulations. Looking ahead, the future of the local group itself looms large. The Milky Way and Andromeda are locked in a slow gravitational dance. Current evidence suggests a merger several billion years from now, but precise measurements of Andromeda's motion will determine the details. If the galaxies collide, their stars will mostly pass unharmed. But their gas, dark matter, and central black holes will interact dramatically. The result will likely be a single, massive elliptical galaxy, an entirely new environment for whatever remains of our cosmic neighborhood. And finally, there is the most profound question of all. Are we alone, even here? The local group contains hundreds of billions of stars and untold numbers of planets. As technology advances, and we begin to probe exoplanet atmospheres for chemical signatures of life, nearby galaxies may one day enter that search. The chances may be slim, but the stakes could not be higher. In the end, the local group is far more than a collection of nearby galaxies. It is a bridge between the smallest and largest questions in science. It connects stellar evolution to cosmology, particle physics to galaxy formation, and observation to theory. By studying it in ever greater detail, we are not merely learning about our galactic neighbors, we are learning how the universe works, how it began, and what our future within it might be. Even now, the James Webb Space Telescope is turning its gaze toward nearby stars, studying worlds that may be capable of supporting life. Future instruments, such as the proposed Habitable Worlds Observatory, will go further still. If living systems exist on planets elsewhere in the Milky Way, the signs may reveal themselves within a single human lifetime. These unanswered questions are not distant abstractions, they're open doors. Each one holds the promise of a revelation that could reshape how we understand the universe. And many of those revelations will emerge from the local group. Yet beyond data and discovery lies a deeper truth. The local group matters not only because of what it teaches us, but because it is home in the most expansive sense imaginable. Home is no longer just a house, a city, or a nation. On a cosmic scale, home is this gravitational family of galaxies that cradles our planet. Our star, our galaxy, and countless others bound together across millions of light years. To understand the local group is to trace our own beginnings. The elements that form our bodies were not born on Earth. They were forged in ancient stars within the Milky Way and in smaller galaxies that long ago merged with it. The iron flowing through our blood, the calcium shaping our bones, the carbon forming our DNA, all were created in stellar furnaces and scattered by supernova throughout this cosmic neighborhood. The cloud that became our solar system carried the ashes of innumerable stars. In a very real sense, we are composed of the history of the local group. Looking forward, the local group also holds our distant future. The slow convergence of the Milky Way and Andromeda will one day transform the entire region. Though this event lies billions of years ahead, far beyond the lifespan of Earth or the Sun, it remains part of our shared cosmic narrative. The story of the local group is inseparable from our own, stretching both backward to the dawn of galaxies and forward into eras yet to come. There is something quietly astonishing in the fact that we can grasp any of this at all. We are small beings on a small world, yet our minds can encompass structures spanning millions of light years. We can weigh galaxies, decode their pasts, and anticipate their futures. This capacity did not arise easily. It is the result of intelligence shaped over deep time, refined through language, mathematics, and science, and extended by tools built across centuries: telescopes, computers, spacecraft. The study of the local group is not the work of a single generation. It is a human continuum. From those who first recognized Andromeda as a separate galaxy, to those who uncovered the hidden realm of dark matter, to the countless researchers whose names are less known but whose contributions endure, this knowledge has been built layer by layer. Today, that lineage continues. Students sift through immense datasets, hunting for faint galaxies. Researchers run simulations that replay billions of years of cosmic history. Engineers design instruments that will see farther and clearer than ever before. All of this effort is driven by something fundamental: the desire to know. There is no urgent practical need to map dark matter halos or reconstruct the lives of dwarf galaxies. and yet the pursuit itself matters. Seeking understanding for its own sake is one of humanity's most profound acts. Along the way, unexpected benefits, emerge technologies, techniques, and ideas that ripple outward into everyday life. But those are secondary gifts. Primary reward is perspective. Knowledge of the universe reshapes how we see ourselves. Faint glow of Andromeda is no longer just a smudge of light, it becomes a vast city of stars. Worlds upon worlds, moving slowly toward an eventual union with our own galaxy. The Magellanic Clouds are no longer mere ornaments of the southern sky, but living systems caught in a gravitational embrace, revealing how galaxies grow and change. Even the galaxies we cannot see with our eyes, the ultra-faint dwarfs carry immense significance, preserving echoes from the universe's earliest chapters. The local group teaches scale. It spans tens of millions of light years, contains trillions of stars, and has endured for nearly the entire age of the cosmos. Against this backdrop, human life is brief. Yet that brevity does not diminish us, it makes our awareness extraordinary. For a fleeting moment, the universe has produced beings capable of understanding it. We are not observers standing apart from the cosmos, or woven into it. Our atoms were born in the Big Bang, reshaped in stars, and assembled on a planet orbiting a star within a galaxy that belongs to the local group. We are participants in the same story we seek to understand. And in recognizing this, something shifts. Our worries shrink, our sense of wonder grows, and our existence here and now feels immeasurably more precious. It is something special, and you've articulated exactly why. The study of the local group sits at a rare intersection of science and philosophy. On the surface, it is about galaxies, dark matter, and cosmic history. But just beneath that surface, it quietly confronts us with questions that humans have asked for as long as we've been able to look up at the sky. Are we alone? Are we unique? What does it mean to exist in a universe so vast? The possibility that other intelligent beings might exist somewhere in the local group is both humbling and exhilarating. With trillions of stars and potentially billions of habitable planets, it would not be unreasonable to imagine that elsewhere, perhaps around a star in Andromeda or a quiet red dwarf in the Milky Way, there are minds asking the same questions we are. We do not yet know the answer, but the fact that the universe allows the question to be asked at all is extraordinary. It tells us that life, at least once, has crossed the threshold from chemistry to consciousness. If we were to discover life elsewhere, it would permanently reshape our understanding of biology, evolution, and our place in the cosmos. It would tell us that life is a cosmic process, not a singular accident. But even if we never find such evidence, the search itself matters deeply. It sharpens our understanding of what life requires, pushes our technology and imagination forward, and forces us to reflect on what makes Earth and ourselves so precious. The local group is not just an object of study, it is our context. It is the environment that made our galaxy possible, the setting in which the atoms of our bodies were forged, the structure that will shape the far future long after humanity is gone. To study it is to place ourselves within the largest meaningful frame available, a frame that stretches millions of light years across space and billions of years through time. That perspective changes us. It reminds us that we are small, but not insignificant. We are not central, but we are capable. One planet among billions, yes, but a planet where the universe has learned to reflect on itself. We live at a rare moment when distant galaxies are still visible, when the cosmic record is still readable, and when our tools are powerful enough to decode it. The story of the local group is a story of connection between galaxies and dark matter, between past and future, between physical law and human understanding. And because we are part of that structure, because our existence is inseparable from it, it is also our story. Each observation, each discovery, each question adds another line to a narrative that began long before Earth formed and will continue long after we are gone. That is the enduring gift of studying the local group. Not answers alone, but perspective. Not certainty, but meaning. A reminder that while we are not alone at the center of the universe, we are participants in something vast, ancient, and profoundly beautiful and capable of understanding it.